Okay, this topic is kind of an addendum to the Lewis structure lesson. Formal charge is not something that's directly tested by the AP exam or by anything you're going to have to do in pre-AP, like a STAR test or anything. But I think it's a good explanation for why some things are the way they are. So a formal charge is a method that we use to decide the best Lewis structure for those atoms that can have expanded octets. The definition of formal charge is a process that determines the efficiency of electron distribution in the Lewis structure. Remember, we followed a set of rules, and we already saw one way that our little step-by-step rules could mess us up with the double bonds and triple bonds having to be added, and the incorrect assignment of a lone pair to a terminal atom instead of a double bond. Well, this is a second way to look at that. So formal charge is also a way to check for possible resonance. So on the right-hand side, then we have some rules to calculate formal charge. Again, you'll need the periodic table. For each element in a Lewis structure, All right, let's go back to this slide. For each element in a Lewis structure, you need to first identify the number of valence electrons that element would have. Pretty easy to do. Then, this is the critical step, we need to subtract from that number the number of electrons assigned to the element in the Lewis structure. On the next slide, we'll do an example with sulfate. But when we count that on the next slide, remember that each non-bonding electron in a lone pair counts. So you just count the dots. And then in a shared pair, which I normally use the line for, I'm only going to count one for those. Another reason I prefer to use the lines instead of dots, just willy-nilly. Oh well, we'll make it work. And then in a double or triple bond, each of those lines will count as one electron. When we find the formal charges, we're going to get number values, positive or negative. What we're hoping for is 0. That means we are in good shape. If we get a positive or negative 1, that's okay. We don't necessarily have to make changes. The molecule, the structure will be okay. Not perfect, but okay. But if we get anything else, positive 2, negative 3, positive 4, anything that's greater than or less than absolute value of 2, that's bad. We have to fix it. That means there's something wrong with our structure. So here's the first example. We're going to use sulfate. I've already got the Lewis structure drawn. And the formal charges are already shown on the structure. I wanted to find a picture of it on the internet without me drawing it in to show you that sometimes or what these values would look like if they were put onto a Lewis structure. But here's how we found it. Starting with the sulfur atom, sulfur has 6 valence electrons. And now as I count the assignment around the sulfur, I see 1, 2, 3 shared pairs. Remember, I'm only going to count 1 electron for each of those shared pairs. So that's why electrons assigned is 4. Subtracting that leaves me with a +2. That's bad. We've got to fix that. First, for the oxygen in this Lewis structure, each oxygen is the same here. I want you to just notice that real quick. So I only have to calculate it once. Oxygen has 6 valence electrons. Now as we count the assignments here, that's going to be, I'm going to pick the one on the bottom. That's going to be 1, 2, 3, 4, 5, 6, and then there's the 7. So there are 7 electrons assigned for a -1. That's okay. It's not perfect, but we could get away with that. But the sulfur is going to require us to do something. So, to fix that, and I've shown you what the structure needs to be to fix it, I'm going to go back to the original structure, and I'm going to show you how we fixed it. We took a lone pair, and who knows why I picked the one on the left, not the one on top. We'll never know. So what we did is we took a lone pair and we reassigned it to a shared pair to make a double bond. And we did that on each side. It makes sense to do them on opposite sides for symmetry. All right, so that's where the two double bonds came from. Now, let's check the math now, see how it fixed itself. If we redo the formal charge for sulfur, we'll see a valence still 6. Now the electrons assigned are 6. Let's count those together. We have 1, 2, 3, 4, 5, and 6. So that's where I got the second 6. Now the formal charge is 0, which is perfect. Now, all my oxygens are no longer the same. I've got 2 oxygens that have double bonds, so let's find the formal charge for those 2 oxygens. Valence is 6. The electrons assigned, let's count those together with the oxygen on top. 1, 2, and then 3, 4, 5, and 6. Now this formal charge is 0. Also perfect. And then finally, we have the single bonded oxygens. Those haven't changed at all, so their formal charge is still -1. Not perfect, but again, with plus or minus 1, we can get away with it. This is the best structure that we could do for sulfate. Some of you might be thinking, well, could we do one more? If we did one more, then your sulfur would go to -1, and while we could get away with it, and that would fix another oxygen, it doesn't fix your central atom, so you're really not accomplishing much. This is about the best we can do for sulfate. Now, just as an aside, I'm not talking about formal charge right now. I'm looking forward, and a lot of you know that sulfuric acid is H2SO4. It's 2 hydrogens bonding with sulfate. Can you guess right now where those 2 hydrogens would bond? If you picked right here, you are correct. A hydrogen ion, the H positive would come and it would form a bond right here with that lone pair on each side of this, and that would be sulfuric acid. So those double bond oxygens are more stable than the single bonded oxygens that have that -1 formal charge, and that prediction really shows what we know to be true for sulfuric acid. Some validation, if you will, for this formal charge structure. All right, as an example, I'm going to work this one with you for phosphate. And let's start from the beginning. With phosphate, phosphorus has 5 valence. The 4 oxygens have 6 each. And let's see, my poor math skills, 24 plus 5 is 29. And we have a -3, so that's 3 extra electrons for 32 total. And that's going to be 16 pairs. All right, so phosphate, we'll put the oxygens around the phosphorus. 1, 2, 3, 4. And then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. They're done. Now the phosphorus here has an octet. So if we just walked away right now, according to the rules, and yes, I do know I forgot the brackets and the -3 charge. We'll take care of that in a bit. But if you walked away right now thinking you're done, you'd miss this problem because phosphorus, while it can only have 4, can also expand. And there are rules for Lewis structures did not account for that. Only formal charge here will show it. So let's calculate the formal charge for the phosphorus. The valence electrons for phosphorus are 5. And the electrons assigned right now, you calculate them real quick. Okay, hope you got 4. So that means the formal charge for phosphorus is +1. Not terrible. Not terrible. We could leave it. How about the oxygens? In this Lewis structure, they are all the same, so I only have one calculation to make. 6 valence minus, why don't you calculate now, or you count the assigned electrons. Yep, there's 7 there. So valence, or the formal charge is -1. Not the end of the world. Could we make it better? The answer to that is yes. I can take a lone pair here, and I can turn that into a double bond. And let's see how the formal charge would change if my structure became a double bond oxygen. Love putting dots. All right, so let's check the formal charge now on phosphorus. It's going to be 5 valence, and now if you count it up, there are 5. 1, 2, 3, 4. There are 5 assigned. So the the formal charge is now 0. And for the double bonded oxygen, it's going to be 6 minus, go over and count them, 1, 2, 3, 4, 5, 6. So that one is now perfect, and the other 3 will stay -1. So we have improved this structure by putting 1 double bond on it. And so phosphate now is going to have 1 double bond. 4 resonant structures. I could have put that double bond on any one of the 4 oxygens. And there we go. All right, I'm going to leave this one with you. Carbonate and draw the resonant structures. And just as a little hint, there should usually be the same number of resonant structures as you have oxygen atoms. All right, give it a try and we'll check it.